Hello, and welcome to this presentation looking at the applications of complex numbers. We're going to consider a few applications here, first of all related to electrical circuitry and RLC circuits, and also related to resolving forces applied at a point to a particular structure. This presentation does assume we've seen previous presentations related to the Cartesian form of complex number and also the polar form of a complex number. The knowledge and techniques reviewed in those presentations will underpin the work we're going to consider here. Presentation overview of complex number applications. We're going to look at resistance, inductance, capacitor circuits, RLC circuits in series initially. We'll look at force resolution, applying forces at a point on a structure or component and calculating the resultant force or the equilibrium force. And we'll look at RLC circuits in parallel. Applications of complex numbers. There are several applications of complex numbers used within science and engineering, such as alternating current theory, as used in electrical engineering, and vector analysis, as used within mechanical engineering. Phasor applications to series connected circuits. The effect of multiplying a phasor by positive j is to rotate it in a positive direction, that is anti-clockwise on an organogram diagram. Don't forget the positive notation on an organogram diagram is anti-clockwise from the real axis is shown here. So multiplying the value on the real axis of 1 by j, we get a positive j value on the imaginary axis. Conversely, multiplying a phasor by negative j has the effect of rotating in a negative direction, which of course is clockwise on the organogram diagram. Thus multiplying 1 on the real axis by negative j gives us a negative value on the imaginary axis as shown. This characteristic is used in AC theory as certain quantities on a phasor diagram reside at 90 degrees to each other, and we'll review these on the following slide. Circuits containing both resistance R and inductance L. Within an RL series circuit shown in figure 11, the inductor voltage VL leads VR, the resistant voltage, by 90 degrees. That is, the current I lags the voltage in the inductor by 90 degrees. So on the organogram diagram shown on the right, this configuration may be written as V, the total voltage, is equal to the voltage in the resistor plus J times the voltage in the inductor, because VL, the voltage in the inductor, is on the imaginary axis. So this is the voltage in the resistor on the real axis, and 90 degrees round on the organogram diagram is the voltage in the inductor. This is the phasor diagram. However, from Ohm's law, the voltage in the resistor is I times R, current times resistance, and VL is equal to I times XL. Thus the voltage expression above could be written as V is equal to IR plus J IXL, but noting that impedance, given the symbol Z here, is actually V divided by I, we can divide this equation throughout by I and write Z for impedance on the left hand side is equal to R plus JXL. So that's dividing throughout by the current I. Inductive reactance XL is defined as 2 pi FL ohms, where F is the frequency and L is the inductance. Circuits containing both resistance R and capacitance C. Within the RC series circuit shown on the right, the capacitor voltage, VC, lags VR, the resistant voltage, by 90 degrees. In other words, the current leads the voltage in the capacitor by 90 degrees. So on an organogram diagram, this configuration is written as the total voltage is equal to the voltage in the resistor on the real axis here minus the JVC, the voltage on the capacitor, shown here on the imaginary axis. Thus, noting the relationship shown on the previous slide, Z in this case can be written as R minus JXC, where XC is the reactive capacitance, and that's defined as 1 divided by 2 pi FC, where again F is the frequency, but C is the capacitance. Example 15. We're asked to determine the resistance and the series inductance or capacitance for each of the following impedances, Z values, assuming the frequency is 50 Hz. So in part A, we've got 5 plus J6 ohms. In part B, we've got negative J22 ohms. And in part C, we've got 12 argument negative 30 degrees ohm. Let's consider part A. So the impedance Z from the question is 5 plus J6. Now, as the complex part of the expression in this case is positive, then that means the imaginary part is a reactive inductance of XL. So from impedance Z is equal to R plus JXL, then the R is read as 5 ohms and the XL is read as 6 ohms. But we know that XL is defined as 2 pi FL. So to find the inductance L, we need to rearrange the above equation. So dividing both sides by 2 pi F, we get inductance L is equal to XL divided by 2 pi F. XL is 6 in the numerator, and in the denominator we get 2 pi multiplied by F, which is 50 in this case. Evaluating, we get 0.0191 henries or 19.1 millihenries. Example 15 continued. This is part B. This time we're given impedance Z of 0 minus J22 ohms. So now the complex part in this expression is negative, so that's a lagging of the resistance, so that's the reactive capacitance XC in this case. So impedance then, Z will be defined as R minus JXC, so by inspection R is 0 in this case, and XC is 22 ohms. So the reactive capacitance XC is defined as 1 divided by 2 pi FC. So if we want to find the capacitance, we have to rearrange for C. So we multiply both sides by the C and divide both sides by the XC. So we end up with 1 divided by 2 pi F XC. Put in the values, get 1 divided by 2 pi F is 50 and XC is 22. Evaluating, we get 0.00014446, or capacitance C is equal to 144.7 microfarad. Don't forget micro is a prefix denoting 10 to the power of minus 6. Example 15 continued, part C. We're given an impedance of 12 argument negative 30 degrees. And this is obviously in polar form, so the first thing we need to do is calculate the impedance in Cartesian form. So noting that 12 argument negative 30 degrees can be written in Cartesian form as 12 cos negative 30 degrees plus J 12 sine negative 30 degrees. Evaluating, we get 10.392 minus the J6. That's now the Cartesian form. We can see here that the complex part of the expression is negative, so it's lagging the resistance in this case, so we've got a reactive capacitance again, XC. So from the impedance Z is equal to R minus JXC, we can read directly that R is 10.392 ohms and XC is 6 ohms. Again, noting the reactive capacitance XC is 1 upon 2 pi FC, we rearrange for capacitance C, so we get 1 upon 2 pi F XC, putting the values in 1 upon 2 pi, 50 again for the frequency, 6 is the XC in this case. We get 0.000531 farads or 530.5 microfarads. Example 16. An alternating voltage, 240 volts and 50 Hz, is connected across an impedance of 30 minus J60 ohms. We're asked to calculate part A, the resistance, part B, the capacitance, Part C, the magnitude and phase angle of the impedance, that's polar form, and part D, the current flowing in the circuit. So given in the question the impedance Z is 30 minus J60 ohms, we note the complex part of the expression is negative, so it's lagging the resistance, so we have a reactive capacitance XC. So the impedance Z is equal to R minus JXC. So for part A, by inspection, resistance R is 30 ohms and XC is 60 ohms. Part B, we're asked to find the capacitance. So knowing the reactive capacitance XC is 1 upon 2 pi FC, we can rearrange the equation to find the capacitance C. That's 1 upon 2 pi F XC. Putting in the values, that's 1 divided by 2 pi multiplied by 50 multiplied by 60, which evaluates to 53.1 times 10 to the minus 6 farads, or 53.1 microfarads. Example 16 continued. Now we can draw the phasor on an argon diagram. We know on the real axis we get 30 ohms, and because this is a capacitance and it's lagging, we get negative 60 on the j-axis. So our phasor resides in the fourth quadrant. So there's our Z impedance. So part C, to calculate the modulus of the impedance, that's Z here, we use Pythagoras theorem. So from the diagram we can see that 30 squared plus 60 squared all square rooted. So that gives a modulus of the impedance of 67.1 ohms. And to find the argument, angle theta, in this case it will be a negative angle theta. I can use this angle theta in here, which will be negative direction from the real axis. So theta is tan to the minus 1 of negative 60 divided by 30. So theta, the argument, is negative 63.4 degrees. So in polar form, our impedance Z is 67.1, argument negative 63.4 degrees ohms. Example 16 continue, part D. We know that impedance Z is defined as the voltage divided by the current. So if we want to find the current in this case, we rearrange for I. So multiplying both sides by I, dividing both sides by Z, I is equal to V divided by Z. In this case, the voltage is defined as 240 volts, argument 0 degrees on the real axis. We divide that by Z. In polar form from the previous slide, that was 67.1, argument negative 63.4 degrees. So in this case, that will be 240 divided by 67.1 for the moduli, and for the arguments we will get 0 degrees minus a negative 63.4 degrees. Be careful of double negative there. So in this case, the current I is equal to 3.577, argument 63.4 degrees. And that's of course in amps for current. Exercise 10. An alternating voltage of 240 volts and 50 Hertz is connected across an impedance of 13 argument negative 67.4 degrees ohms. We've got to calculate A, the resistance, B, the capacitance, C, the current flowing. Answers are given in the brackets on the right hand side. I encourage you to stop the presentation and attempt exercise 10 before reviewing the solutions on the following slides. Exercise 10 continued. We now know that Z in Cartesian form is 5 minus J12. So noting that the complex part of the expression is negative, thus lagging the resistance, we have a reactive capacitance XC here. So from the impedance Z is equal to R minus JXC. Part A, we read by inspection, the resistance R is 5 ohms and XC is 12 ohms. Part B, we've got to find the capacitance. Well, we know the reactive capacitance XC is 1 divided by 2 pi FC, so rearranging for capacitance C, that's 1 divided by 2 pi F XC. Putting in the values, 1 divided by 2 pi multiplied by 50 multiplied by 12 in this case for the XC, evaluates to 265.3 times 10 to the minus 6 farads, or 265.3 microfarads. Exercise 10 continued, part C. We're asked to find the current in part C. So from the impedance, Z is equal to V divided by I. We rearrange to find the current I, so multiply both sides by I and divide both sides by Z. We get I is equal to V divided by Z. The voltage is 240 argument 0 degrees, and the Z is 13 argument negative 67.4 degrees. So don't forget, when we're dividing complex numbers in polar form, we divide the moduli and subtract the argument. So in this case it's 240 divided by 13 for the modulus, and there's argument of 0 degrees, and we're taking away here the negative 67.4 degrees. So I in this case is 18.5 argument 67.4 degrees, and that's amps. Example 17 is a mechanical orientated problem. We're asked to calculate the magnitude and direction of the resultant force of the three coplanar forces shown in the sketch when they act at a single point being here. We're also asked to state the equilibrium force, which is simply the equal and opposite force to the resultant force. So in this case we're given three coplanar forces. That just means they're in two dimensions. They're actually concurrent forces because their lines of action all go through the same point 0 here. So force 1, F1, is given as 12 newtons. That's an angle of 40 degrees positive from the real axis is shown. F2, shown here, is 8 newtons, and that's an angle of 125 degrees positive from the horizontal axis. And F3, force shown here, is 15 newtons, and that's shown as 150 degrees from the real axis, but that's in the opposite direction, so that's actually a negative 150 degrees in terms of angle theta. If we write the three forces down in polar form, we've got F1 is 12 argument 40 degrees from our diagram. F2 is 8 argument 125 degrees, reading the diagram, and finally F3 is equal to 15 argument negative 150 degrees because it goes in the opposite direction to the positive theta direction. Example 17 continued. From the Argand diagram we've got three forces stated in polar form. We want to find the resultant force. We want to find it in actually Cartesian form, you'll see in a moment. So what we're going to do is add up our three forces. So our resultant force will be 12 argument 40 degrees added to 8 argument 125 degrees added to 15 argument negative 150 degrees. Now don't forget, very important to remember, we cannot add complex numbers in polar form, only in Cartesian form. So we need to convert to Cartesian form here. So on the left hand side we'll get our Cartesian form for the resultant force of x plus jy. So taking the first force of 12 argument 40 degrees, to convert to polar form that will be 12 cos 40 degrees plus j 12 sine 40 degrees. Taking the second force of 8 argument 125 plus 8 cos 125 degrees plus j8 sine 125 degrees, and taking the third force, 15 argument negative 150 degrees, that will be then plus 15 cos negative 150 degrees plus j15 sine negative 150 degrees. If we now evaluate that expression for F1, we'll get 9.1925 plus j 7.713. For the F2, we'll get negative 4.5886 plus j 6.553. And for the F3 force, we'll get minus 12.9904 minus j 7.5. All we do now is add up the real and add up the imaginary components to get the x plus jy component. So adding the real components up, we get negative 8.3865, and adding the imaginary components up, we get plus j 6.766. So there's our resultant force in Cartesian form. Example 17 continued. Now we're going to convert from Cartesian form to polar form. So plotting our resultant force on an Argand diagram, on the real axis we get negative 8.3865, on the imaginary axis we get positive 6.766. So our phasor resides in here, our force vector, if you like, resides in here on the second quadrant of the Argand diagram. Don't forget theta angles are always measured positive from the real axis in an anti-clockwise direction. So first of all, working out the modulus of the resultant force F. So the modulus is 8.3865 squared plus 6.766 squared, all square rooted. That's Pythagoras theorem. So the modulus is 10.8 newtons in this case. In calculating the argument theta, and don't forget that theta must be measured from here around. So that's the angle we'll be looking for on the Argand diagram. So to calculate angle theta, first of all I'm going to calculate angle alpha, shown in the diagram here. And angle alpha is tan to the minus 1 of the opposite side, 6.766 divided by the adjacent side, 8.3865. That gives an alpha value of 38.9 degrees. And we can see by inspection of the Argand diagram, we've got to take alpha from 180 degrees to get theta. So theta in this case is 180 degrees, take away the 38.9 degrees. So angle theta is 141.1 degrees. So our resultant force Fr is written in polar form as 10.8 argument 141.1 degrees, and that's newtons. Now the question finally wants us to state the equilibriant force, the equal and opposite force to resultant force. Now on the Argand diagram that will simply be drawn opposite the resultant force, so in this position here. So to state that in polar form is simply going to be 10.8 argument 141.1 degrees plus 180 degrees. So it's 10.8 argument 321.1 degrees. That's newton. And the 321.1 degrees would of course be this angle in here. Just a brief note about resultant forces and equilibriant forces. When we're finding the resultant force in Cartesian form x plus jy, the equation can be stated like this. X plus jy on the left hand side is equal to the summation of the forces in Cartesian form on the right hand side. When finding the equilibriant force, the x plus jy equation can be stated as 0 equals to x plus jy and then plus the other forces applied in Cartesian form. Because if we include the equilibriant force into our system of forces, then the system is in equilibrium and it should equate to 0. So subtly different ways of finding the resultant and equilibriant force, but essentially you can find the resultant force and just reverse the direction of this to find the equilibriant force. But I thought I'd mention that in passing. There's two different ways you can approach the problems depending on what you ask for in the question. Exercise 11. We're asked to write the four forces shown in the sketch as complex numbers in polar form. Then we're asked to show that the four forces are in equilibrium. In other words, when we add up all the horizontal and vertical components, or the real and imaginary components in complex terms, they should equal to 0. So we need to show that. So I'd encourage you first of all to write down the complex numbers in polar form, convert to Cartesian, add up the real and imaginary parts, and you should find they all come to 0. I would encourage you to stop the presentation and attempt that exercise now before reviewing the solution on the following slide. Exercise 11 solution. So we're given four forces applied to this point here, and we have to show that the forces are in equilibrium. So in other words, when we add up all the forces, the out of balance force should be 0. So to do this, I'm going to write down initially my forces in terms of polar form, the force equals r argument theta format. I'm going to convert them into Cartesian form and then add up the real and imaginary components, and they should equal to 0. So considering each force one at a time, 2.6 kilonewton is shown here in the horizontal direction. The angle theta there would be 0. Don't forget to measure angle theta is positive from the real axis in anti-clockwise direction. So our first force in polar form is 2.6 argument. Don't forget, when we write that into Cartesian form, we write it as x plus jy, and that's r cos theta plus jr sine theta. So in this case that will be 2.6 cos of 0 degrees plus j 2.6 sine 0 degrees. That evaluates to 2.6 plus j0 for the first force. Taking our second force, which is 2.5 kilonewtons vertically up, that will be an angle of 90 degrees in an anti-clockwise direction from the real axis. So in polar form, that's 2.5 argument 90 degrees. So don't forget, when we're talking about the angles, it's this angle in here is the 90 degrees we're referring to. So convert that into Cartesian form. That will be 2.5 cos of 90 plus j 2.5 sine of 90. Again, evaluating that, you'll get 0 plus the j 2.5. Taking our third force, which is 3 kilonewtons shown here, angle 30 degrees is shown. That in polar form will be 3 argument 150 degrees. And again, don't forget the angle is measured from here around to there. So that's the 150 degrees that we're referring to. So in Cartesian form, that will be 3 cos of 150 degrees plus j 3 sine 150 degrees. That evaluates to negative 2.598 plus j 1.5. And the final force to consider is 4 kilonewtons vertically down. So in polar form, that can be written as 4 argument negative 90 degrees. So if I want to, I can specify my angle this way round, and that will be a negative 90 degrees. If you want it in the positive sense, it will be 270 degrees. But I'm going to use the negative sense here. So in Cartesian form, that becomes 4 cos of negative 90 degrees plus j4 sine of negative 90 degrees. That gives us 0 minus j4. If we add up the x components and the jy components, we find that they both go to 0, which is what we would expect if the forces are in equilibrium. Exercise 12 shows us an eyeball, and it's designed to withstand the forces from 4 cables applied simultaneously. We're asked to determine the resultant force for this system of forces, and again to state the equilibrium force, which is the equal and opposite to the resultant force. So 4 forces shown here, all applied at the same point, so they're all concurrent forces, they're coplanar forces because they're in the same 2 dimensions here. So we've got to work out the resultant force and then the equilibrium force. I would encourage you to stop the presentation and attempt exercise 12 before reviewing the solution on the following slide. Solution to exercise 12. So what we're going to do here is to write the 4 forces in polar form, the r argument theta format, convert this to Cartesian form, and then add up the real and imaginary components to find the resultant force. So considering our first force of 4 kilonewtons shown at the 40-degree angle here, in polar form that would be 4 argument 40 degrees. If we put that into the Cartesian form, then that's 4 cos of 40 degrees plus j4 sine 40 degrees, and evaluating that we get 3.064 plus j 2.571. Considering the second force, which is the 2 kilonewtons shown at 20 degrees from the vertical, now in polar form that will be 2 argument 110 degrees, in other words that's 90 degrees plus 20 degrees, because again we always measure our angles from here around, so the 110 degrees is around to here, positive sense. If we evaluate that in Cartesian form, that will be 2 cos 110 degrees plus j2 sine 110 degrees, and evaluating that is negative 0.684 plus the j 1.879. Considering our third force here applied to the eyeball, this one here is 3 kilonewtons, it's 30 degrees from the vertical shown there. So in polar form that's 3 argument 240 degrees, that's 30 degrees away from the 270 degrees. So on the Argand diagram, the angle we're plotting here at the 240 degrees is round to here. If we now convert that into Cartesian form, that will be 3 cos 240 plus j 3 sine 240, evaluates to negative 1.5 minus the j 2.598. And finally, the last force to consider is the 5 kilonewton force, and in polar form that will be 5 argument negative 50 degrees. I'm using the negative theta angle in this particular case. So converting that into Cartesian form, that would be 5 cos negative 50 degrees plus j5 sine negative 50 degrees, evaluates to 3.214 minus the j 3.83. If we now summate the columns there for the x and the jy components, we get 4.094 for the real axis, the horizontal axis, and minus a j 1.978 on the imaginary axis. Exercise 12 continued. So from the previous slide, the resultant force, I've called it Fr here in Cartesian format, was 4.095 minus j 1.978. These two components, so real and imaginary, can plot on an Argand diagram to form a right angled triangle. So on the real axis we get 4.094, on the imaginary axis we get negative 1.978, so our resultant force vector is shown here in the force quadrant. We now need to work out the magnitude of the Fr and the angle theta. So to convert from Cartesian to polar form, the modulus r, which is the length of Fr in this case, is found from Pythagoras' theorem. So in this case it's 4.094 squared plus 1.978 squared, all square rooted. So the magnitude of Fr is 4.547 kilonewtons, and the argument is tan to the minus 1 of negative 1.978 divided by positive 4.094. That gives an argument of negative 25.8 degrees. So our resultant force, Fr, in terms of polar form, our argument theta, can be written as 4.547 argument negative 25.8 degrees, and that's in kilonewtons. The question also wanted us to state the equilibrium force, and that's equal and opposite to the resultant force. So in this case that will be 4.547, and adding 180 degrees to negative 25.8 will give us an argument of 154.2 degrees. So in other words, the equilibrium force would be in this sense here, opposite to that of Fr. Here are some tutorial questions I've encouraged you to attempt. Question 49. We're asked to determine the resistance R and the series inductance L, or capacitance C, for each of the following impedances, the Z values. We're given 6 questions here from A through to F. Be careful to determine which is the inductance and which is the capacitance in these particular questions, and also with the last couple of questions make sure you convert them into Cartesian form. They're currently stated in polar form. Answers are given in the square brackets below. Tutorial questions continue. Is question 50. We're given an alternating voltage of 100 volts and 50 Hertz is applied across an impedance, our Z value, of 20 minus J 30 ohms. We've got to calculate in part A the resistance, in part B the capacitance, part C the current, in part D the phase angle between the current and the voltage. I would encourage you to sketch the impedance on an Argand diagram so you're clearly sure which phase angle you're calculating. The answers are given here in the square brackets. Question 51, we're given two voltages represented by 15 plus J10 and 12 minus J4. We're asked to determine the magnitude of the resultant voltage when these are added together. So we've got two voltages here given in Cartesian form, so we can simply add the real, add the imaginary parts, and then work out the magnitude of the resultant voltage given here in brackets. Tutorial questions continued. Question 52. We're given two impedances denoted as Z1 and Z2. They are connected in series and a supply voltage of 100 volts is stated. We're asked to determine the magnitude of the current and its phase angle relative to the voltage. So again we will need to add up the impedances, find the resultant of the impedances, and then from Z is equal to V divided by I, we can find I by transposing the equation, and then we can find the phase angle. So again, I strongly encourage you to sketch the resultant phasor on an Argand diagram so you clearly know which phase angle you're calculating. Answers are shown in the square brackets. Question 53. A resistance of 45 ohms is connected in series with a capacitor given as 42 microfarads. We're given the applied voltage 250 volts and 50 hertz. Got to determine A, the capacitive reactance, B, the impedance, C, the current and the phase relative to the applied voltage, D, the voltage across the resistance, and E, the voltage across the capacitance. So in this case, part A, we can find the capacitive reactance. We know the formula for XC, and we're given the F and the C in the question. Once we've calculated the capacitive reactance and we know the resistance in the question, we can find the impedance from Pythagoras' theorem. And in part C, we can find the current. The I is equal to V divided by Z. And we can find the appropriate phase angle. Again, make sure you sketch the phase on an arcane diagram. Part D, we can calculate the voltage across the resistance from V is equal to IR. We know the resistance in this case, we've calculated the voltage. And then part E, we can calculate the voltage across the capacitance. Knowing that XC is equal to V divided by I, we can transpose to find the voltage across the capacitance. Answers are given in the square brackets as usual. Tutorial questions continued. Question 54 relates to force resolution. We're given forces of -3 minus J5 newtons, 13 plus J2 newtons, and -8 plus J4 newtons, and an equilibrium force of X plus Jy in newtons. These forces are in equilibrium, so when we add them all up, we should find they come to 0. So to do this, we're going to generate an equation that equates to 0, and we're going to add up all the real and imaginary parts, and we'll find from that the X and the Y values. Answers are given in the square brackets here, and that's the equilibrium force given. Question 55, we're asked to find the resultant force of forces given, F1, F2 and F3, all in Cartesian form. Because we're finding the resultant force, we'll generate an equation as X plus Jy equals to F1 plus F2 plus F3. We'll add up all the real and imaginary parts on the right hand side. We can then equate the real parts to X and the imaginary parts to Y. I would encourage you to plot the resultant force on an arcane diagram to help you calculate the resultant force in polar form. You clearly need to know which quadrant the resultant force resides to work out the appropriate angle or argument. Answers given in square brackets here. Question 56, a body moves from point 0 plus J0 to point A, 9 minus J10. It then moves to points B and C, given here respectively 22 plus J4 and -7 minus J. We've got to determine the distance from the origin, the 0 plus J0 in this case, and the angle relative to the real positive axis. So as the origin is given as 0, 0 here, we will basically add up the real and imaginary parts for A, B and C, find the modulus of these and the argument. And again, I would encourage you to sketch this resultant distance on an arcane diagram so you clearly know which argument you are calculating. The answers in polar form are given here in the square brackets. Example 18, we're now going to look at a parallel circuit as opposed to in the previous examples in questions series circuits. So for the parallel circuit shown on the right hand side, we're asked to calculate the value of the current I and its phase relative to a 240 volt supply. And we're going to use complex numbers to solve this problem. So the circuit on the right hand side contains 3 parallel impedances. I've labelled them as Z1, Z2 and Z3. So Z1 is 4 plus J3, so this relates to this part of the circuit. The R1 equals to 4 ohms and the XL is equal to 3 ohms. Don't forget here the real part is the resistor 4 and the imaginary part is the inductance, and that's reactive inductance XL, and that's 3 ohms. And that's leading the resistance, so that's plus in this case, so that's 4 plus J3 in Cartesian form. Considering now what I've called Z2, that relates to this branch here. The R2 is equal to 10 ohms. There is no inductance or capacitance in this branch, so that's simply 10 for a real number plus 0 and J. That again is in Cartesian form. Finally, Z3 relates to this part of the circuit. I've got an R3 for the resistance of 12 ohms and a reactive capacitance XC of 5 ohms. So that's 12 minus J5 in Cartesian form. Now, as this is a parallel circuit, to work out the impedance for the circuit, we have to use the formula 1 upon Z is equal to 1 upon Z1 plus 1 upon Z2 plus 1 upon Z3. And notice for reference, our voltage is given as 240 volts and our frequency is 50 Hz. The appropriate calculation is shown on the following slide. Example 18 continued. So we're going to write the previous expression, the 1 upon Z equals 1 upon Z1 plus 1 upon Z2 plus 1 upon Z3, in terms of what's called admittance, symbol Y, where admittance is equal to 1 divided by impedance, 1 divided by Z, and it has unit Siemens. So now writing the previous expression in terms of admittance, we get Y is equal to Y1 plus Y2 plus Y3. So we're going to calculate the Y1s, Y2s and Y3s individually. So to evaluate Y1, Y1 is 1 upon Z1, or in this case 1 upon 4 plus J3. Now this is in Cartesian form, so we need to solve it using the complex conjugate method we looked at in the previous presentation. So here we've got 1 upon the 4 plus J3, so denominator has a positive for the imaginary component, so the conjugate will be 4 minus J3. So multiply top and bottom of our fraction by 4 minus J3. If it helps, you can think of brackets being used here to help you with the binomial expansions. There are brackets of course around the top, but we need them there. And then multiplying the top, in this case we've just got 1 multiplied by 4 minus J3, so 4 minus J3 on the top. And don't forget on the bottom we've got a binomial expansion, so we get 4 multiplied by 4, so that's 16. 4 multiplied by the negative J3, so that's negative J12. Then we get plus J3 multiplied by 4, so that's plus J12. And then plus J3 multiplied by the negative J3, so that's negative J squared, 9. Just be careful there of the negative terms. Simplifying, we get 4 minus J3 in the numerator, and on the bottom notice that these two terms cancel. They should always cancel when you're multiplying by the complex conjugate. So on the bottom we get 16 minus a negative 1 times j. And that negative 1 is for the j squared term. Again, from the previous work, we know that j times j is real number negative 1. So simplifying again, we get 4 minus j3 on the top, and on the bottom we get 16 plus 9, so that's 25. Double negative here, be careful. So y1 in this case is 0.16 minus j 0.12. And that's admittance. Y2 is a simpler calculation in this particular case. We've got 1 upon Z2, and 1 upon Z2 is 1 upon 10 plus J0, so that's simply 1 upon 10, or 0.1 Siemens. Finally, Y3 is 1 upon Z3, in this case it's 1 upon 12 minus J5, so again we've got a complex conjugate problem here, so we're going to multiply top and bottom of our fraction by 12 plus J5, so that changes the sign on the imaginary part. And again, if it helps, you can think of top and bottom of the fractions as being in terms of bracketed terms. That helps you with your binomial expansion. I will let you undertake the binomial expansion this time. Just be careful with your negative terms and so on. Again, you will find that the two imaginary terms on the bottom of the fraction will cancel if you get your calculations correct. When you simplify, you'll end up with 12 plus J5 divided by 169 in this case. Again, watch out for the J squared term, that's the negative 1 term. You get double negatives again. So Y3 should evaluate to 0.071 plus J 0.02959. So now to find the total admittance, the total Y, we simply add the above Y1, Y2, Y3. So here's Y1 from above, we add that to Y2 from above, and then add that to Y3 from above. What you should find is your total admittance is equal to 0.331 minus J 0.09041, and that's in Siemens. Example 18 continued. Now we're going to convert the previous admittance that was in rectangular or Cartesian form now into polar form. I plot it on an Argand diagram so I clearly know where the phasor resides. It's 0.331 on the real axis and negative 0.0904 on the imaginary axis, so our phasor resides here, so that's the total y in this particular case. So to find the modulus of the admittance, that's the y in this case, we use Pythagoras theorem, so that's 0.331 squared plus 0.09041 squared, all square rooted. So the modulus of the admittance is 0.343 ohms to the negative 1, or 0.343 Siemens. And to find the argument, angle theta, and don't forget that the angle theta in our case will be measured this way round, so it'll be a negative theta value, so our theta is going to be in here, and it's going to be a negative value. That will be tan to the minus 1 of the negative 0.09041 divided by 0.331. So theta is negative 15.28 degrees. So our admittance, y in polar form, is stated as 0.343 argument negative 15.28 Siemens. Now we know that current I is given as V divided by Z, but as we're using admittance here, that will be the same as V multiplied by Y, because Y is 1 over Z. So in this case, the voltage is 240 argument 0. We're multiplying that by the admittance Y of 0.343 argument negative 15.28. Don't forget, when we're multiplying in polar form, we multiply the moduli and add the argument. So be careful here. That's 240 multiplied by 0.343. And for the argument, that's 0 plus, and then we've got a negative 15.28. So be careful there for your sign. A positive and a negative makes a negative. So finally, I is equal to 82.32 argument negative 15.28, and that's amps. I'd encourage you to stop the presentation and review these slides for example 18 again before attempting the question on the following slide. Question 60, we're shown a parallel circuit within which we have to calculate the current I flowing and determine the phase angle relative to the applied voltage. So it's a very similar question to that shown in the previous example. I'd encourage you to attempt this question based on the solution on the previous slide. The answer is shown in the square brackets. Here's the bibliography used to help generate this presentation. Again, I would strongly encourage you to refer to some of these textbooks, some very good textbooks. I hope this has been of interest to you, and thank you for viewing.